Okay. Okay. Does it work, the mic? I don't know. Yes, I think so. Okay, so I'm talking about finding bugs in open source system software using a tool that we've developed, which is called Coccinelle. Wrong one. It's okay. It's okay. Everything's okay. So bugs, everyone knows bugs are everywhere. So what we're interested in particular is bugs in the Linux kernel. So Linux is, as everyone knows, quite important software. It's used in all kinds of systems. It's also extremely large. There's over 14,000 C files. And earlier today, Andrew Tannenbaum told us it was 6 million lines of code, but actually when I tested the most recent release, it was 8 million lines of code. So it's growing at a quite rapid rate. I say it's increase of almost 50% since 2006. It could even be more than that. Linux also has a property as an open source system of having more experienced developers, the kernel maintainers, less experienced developers who just want to contribute one particular fix or feature. And there's also the developers of proprietary device drivers who maybe they're more expert in the properties of the device than they are in the Linux kernel itself. So what the effect of this is, the effect of all of this change and all of these different people contributing, is that bugs are entering the Linux code, they are maintained in the Linux code, and then maybe a whole bunch of them get fixed, but then they come back. So we'll look at one which has, it says, the comment says strikes again, so you can see that it's something that has come up from time to time. And here the bug is, this is something that's allowed in C. It's not allowed in C++, or there was at least a warning about it in C++. But what we have is we have a mixture of a binary operation here. So this is a Boolean operation. So this is either a negation. So the result of it will either be true or false. That is either 1 or 0. And here we have a bit AND operation. And if you bit AND maybe either 1 or 0 with, for example, an even number, then the result is always 0, and the test is always going to be false. So that's probably not what was intended. What was intended is that we take this expression, we see what its bits are, we see how they correspond to the bits of the constant, and then we take either true or false of that. So the solution is quite simple. We just take the original expression and we put some parentheses in it. So we can see here how this bug has appeared and disappeared. Actually, it's perhaps not so visible, but there are light blue lines. So here we have a whole big light blue region here, which is places where the bug existed. So what we've done, we've developed a tool, another tool in our group, which is called Herodotus, which correlates occurrences of bugs in different versions so that you can see this is the same bug even though it has moved into different places due to other things being added and removed in the code. So we see lots of occurrences of the bug here, and then at this point they all get fixed. Actually, there's a line here where there's a version where there's none of these bugs left. But then you can see over here that they creep back into the code. And these black lines means places where the kernel, where the particular file didn't exist. So what has happened is the bug was fixed in all of the existing files, but new code has been added, and that code has the bug in it again. So what we need is some kind of automatic way of finding and ideally fixing bugs. So that's part of the goal of our tool, Coccinelle. So it has two features. One of them is we provide a static analysis that matches patterns in C code. And the other feature is that we can also specify transformations. And so once you write a pattern that recognizes a bug, then you can express how to fix that bug as well. Even if it's a simple fix, just like adding those two parentheses, perhaps you would be happier that a tool should do it and that you could check the result of that tool rather than adding those parentheses yourself and perhaps making some kind of mistake. So the important point is that our approach is user configurable, and it's based on the patch notation. So basically, you can write things that look like patches, that look like real code. You have some code you would like to find, but the problem with normal patches is that they're very specific to a specific particular place in the code. They refer to maybe particular variables. They have a particular amount of white space in front of them, and so on. So the goal of our tool is to allow you to express things at the code level in a patch-like way, but maybe make them a little bit more abstract and so that they can be applied more generally. So here's an example. This is how we can find and fix that bug that I just showed you. Basically, our idea is that we have a Boolean negation operator, and we have a bit AND operation. And basically, the argument of the Boolean negation operator can be any arbitrary expression. So what I've said is that E is a variable, and it can match any expression. And if you look around a bit in the kernel, you find that often this problem occurs when the other argument of AND is not, the bit AND is not an arbitrary expression, but it's actually a constant. And so we're going to specify that, because actually if you had two expressions, you might want to actually be doing an AND of two Boolean operations. So basically we say we have this pattern, and we would like to replace it by basically the same code, but with the parentheses before and afterwards. So basically what our tool does is it takes this pattern, it searches through your entire code base. It can be Linux, it can be any other C code, and it finds every occurrence of this pattern, and it modifies it like that. So it doesn't have to, unlike a normal patch, it doesn't have to appear on a specific line. This doesn't have to be a variable called E, and so on. So we can see an example. So here's a particularly pathological example. In this case, the person decided for some reason to put a new line here after his little arrow. And so we have the exclamation point, the Boolean negation operation, and the AND being on different lines. So if you were just going to do a grep and try to find all the lines that have exclamation point and AND, then you wouldn't find this particular case. So we have the semantic patch, and the E is going to match this expression here, and the C is going to match this expression, and then it will recreate that term according to this rule. And so we get this out as the answer. Okay, so this is just showing the diagram we had before. So using this, we could have, if we had perhaps applied it back here at this time, we could have fixed all of those bugs at once with no particular manual effort at all, except that you would like to go and check that the result that you produce is okay. So this number of them declined after a while, but still in October 2009, there were still 2 that exist. And I think there's still 2 that exist today as well. One of them has just been sitting there. I've reported it, but no one has fixed it. So look at another example, which is a little bit more complicated. So this is a bug that was found last summer, and it was, someone showed how you could exploit this bug in order to become root. So it might look quite simple, but it has some impact. So here the issue is we have a parameter which is called tune. We have a local variable which is defined to be a dereference of that parameter. And then we have a null test on that parameter. And then we have the rest of the code. And certainly, I mean, we have 2, this is contradictory here. Either the null test is useless because tune can never be null, or the null test is useful and this code here is going to crash. So the solution to this problem is to not do the reference here, and instead move the initialization to after the null test, and then it becomes safe. So if we want to specify finding these kinds of bugs using our notation, basically we have the basic idea, which is that you have a dereference and then you have a null test. So what I have made is a pattern here. We say X is going to be an arbitrary expression, and field is going to be an arbitrary field name, any kind of identifier. And basically this should come at some point, and then somewhere later in the code, the null test should appear. So this ... notation here means some unknown code occurs in between the two, and actually there's an execution path that will get you from here to here. So it's not just a syntactic notation. And these little stars mean I don't have any particular transformation I want to perform. I just want to be informed about the presence of these things. Okay, so if we take this and we apply it to the entire Linux kernel, we get a lot of reports. I think there's 300 and some of them. But if we start studying them, we find out that a lot of them are actually not bugs. So here's an example. So in this case, we have bridge arrow bus, and then we have a null test here on bridge. But this is not actually a bug because bridge has been redefined in between them. Okay, so one thing we could do is we could just look through those 300 bug reports and filter out the ones that are not okay. Another thing we could do is we could try to refine this specification so that it would find everything except this one. And another thing we could do, which is quite useful to do in practice, is to think about a special case where the specification is more likely to always give you the right answer, and then you can work on that. And then you can write another specification later and find some other bugs, the ones that got left out. So that's what we're going to do. So we can think back to the original problem, which was that we had a variable declaration, and then we had a null test right at the beginning of the function. So this rule is trying to capture that. Here I say we have some arbitrary type, some arbitrary identifier, and it's being initialized to some dereference. So this is our initialization. Then I say, in between this initialization and the null test here, there's no reference to E and there's no reference to I. So I want to be sure that the code is in a good way, something that where nothing can go wrong. And then everything it will tell me will be a correct change, and then I can go off and submit them to Linux. So what we do here, in this case, we know exactly also how to fix the problem, which is an advantage. In this case, the solution is just to take the initialization and move it down after the null test. Okay, so if we apply this more constrained rule, we can see again, a long time ago, there were lots of these sort of bugs. This is a problem that can cause your machine to crash, and so it's not surprising that they have gotten fixed slowly over time here. But then if you look on the other side, if you look at the top of the graph here, they have been added over time as well. So sometimes they're added because new files are added, as an example we saw before, and sometimes some of these don't have any have white space to the left, which means that the code was changed in some way to add the bug. Okay, so in conclusion, we have developed a patch-like program matching and transformation language. So you can write your specification in something that's very, very close to C code. There's not a lot of different APIs to learn. We've used this to create over 450 patches, which have been submitted into Linux. Some other Linux developers have been using this, sometimes not without asking us very many questions. So I think it should be very easy to get started with. And we've also found, we haven't worked very much on other software projects, but we have looked in some detail at various things, especially OpenSSL, VLC, and Wine. So questions? Yes? So the question is, do we support C++? And the answer is unfortunately no. So also, any other language you'd like to ask about? Unfortunately, we don't support it. We just only C.
Is there a way to detect an error in a function you call under certain conditions?
Yes, so you could you could write one rule that describes the conditions in which you call that function, and then you can write another rule that that shows the body of that function, and then has the error pattern inside of it. So you can write multiple rules, and those rules will apply at different places in your file.
Would it make sense to, if you have a rule file for rules that you want to apply,
Mm-hmm.
to be able to feed them to GCC or other compiler, so that as you work on code, anything that this highlights will turn up as you go?
So the question is, should we integrate this into GCC?
Make it an option in GCC.
Or make it an option in GCC so that it could be checking your code every time you compile it?
Against whatever rule file you have.
Yes. So it would depend to some extent on the reliability of your rule file, whether it would be desirable or not. So the rules that I actually showed are things that have a very high chance of finding real bugs and fixing them in the proper way. But other rules, I mean, it just does what you tell it to do, and so other rules have maybe 50-50 chance, and so maybe you don't want to be bothered with that every single time. So we haven't. An idea would be to instruct the tool: this one is a real bug, this is not a real bug. Don't bother me about it anymore. But we haven't worked on that yet. So, I think there are some questions over here.
How many rules do you have now? Just to understand,
Sorry, I have absolutely no idea. I don't know. Sorry, what?
Are there lots of rules already defined for them?
There are a number of rules on our website, but you can also write any rules that you want by yourself. So it's not a black box sort of tool.